Oh, hello. Whoops.
All right. Can I ask you, just because I know there are some first views here, can you tell us, can you point to the POVM on here? Then can you point to the crowd software and just name these things for the young ones?
Oh, okay. Yeah, so these two things are called POVMs because they resolve the identity. In particular, the POVM is the set of elements in the sum, okay? So each of these is a POVM element, and there's the whole sphere of POVM elements, yeah, or a whole plane of POVM elements, okay, yeah. And these are fancy names for the 7-dimensional manifolds I'll be talking plenty about. And yeah, and this cloud again was just in reference to how to interpret the differential measuring process.
And these elements are outcomes, right?
And these elements are what happened, yeah, yeah. So unlike, you measure the colors coming out of an atom and you see these quanta, you're measuring the energy changes. You don't see quanta in this case, you don't see quantized values, you see everything, potentially. Yeah, what's up?
You have to
Oh, I'm sorry. Got it, thank you. Okay, so can I go on?
Yeah.
Do. Wait, what just happened?
The time inverse, I think.
Indeed. Apparently I go this way, then I'm in here. There we go.
Sorry, back one slide. Just tell them, can you tell them what a Krauss operator is, too? Since we've got one here.
That's later.
Later,
yeah.
Great. Yeah.
So I should have said, this talk comes in 5 phases. We've just finished the introductory part, which was just supposed to give you guys a flavor of what this whole talk is even about, okay? So that you hopefully don't get lost because we're about to go into some technical depth, okay? Yeah, so here's a picture of Gold Beach, Oregon. It's a very humble little town, but I've been living there ever since the pandemic started. Yeah. I just thought I'd show it to you because it's nice for me to look at. It's home right now. And yeah, I just showed you guys a lot, so take a little breather. Okay, so the next thing we're going to talk about is advanced measurement theory. Sure. What's up, Carl?
Chris is the most famous physicist living on the north side of Gold Beach.
There is no university there. So.
You might ask what. So.
Oh, on this, I'll tell you guys that later. It turns out that Carl's PhD advisor lives in Gold Beach also, which has been like, oh my God. Yeah. So, okay. Okay, so this is how I like to step into advanced measurement theory, okay? Which is to say, if you've ever calculated anything in quantum field theory, like a cross section, you might have come across this idea of sum over final states, average over initial states, okay? And something I like to step into is to actually point out all this work on advanced measurement theory can be thought of as just formalizing this structure that's behind sum over final states, average over initial states, okay? So since there's a bunch of first years, I thought I could go through this with you guys. So this is the so-called system meter interaction model of an advanced measurement, okay? It's an indirect measurement because what we're gonna do is take a meter, which is classical. You don't do crazy superpositions and worry about commutativity, etc. You just have something like a line of positions and the meter starts pointing at 0, and then we're going to displace it either to the left or right, depending on an interaction with some observable that is quantum. Okay. So given this problem, if you know a little bit of quantum mechanics, there is an algorithm for how to calculate the probability of seeing this and this, given all of that. Okay, so this should look like a pretty normal kind of probability calculation if you know some quantum. Okay. Given that the system is prepared in size 0, and just completely taking for granted, but also given that the meter is some state, some interaction occurs, and then what is the probability of observing X in the register and psi 1 in the system? Okay. So do I want to jump in? Yeah, I've already started. So, okay, simple linearity.
Hey, Chris.
Yeah.
So what do you mean by observing the system? Because aren't you using the register to observe the system in the first place?
Would you ask?
So when you're saying like stopping observing register in state X and system in state psi 1, aren't you, you're kind of using the register to infer any properties about the system?
Right, yeah, so right now I'm kind of pretending I'm doing a measurement on the system also.
Okay.
But just because that would be a probability you can calculate. Yeah, but I guess, yeah, it should be important to notice that in actuality, you're imagining that this system doesn't get directly measured. Does that address your concern?
Yeah.
Okay. Okay. Okay, so let's just walk through what's behind this. So I can just use linearity to rewrite this as a trace over the system in meter. And then if I wanted to just calculate the probability of X given some distribution of psi 0, right, then this is the old average over initial states, sum over final states. Okay, okay, so you just apply linearity. So this psi 0 can go over here, and all of the psi 0 dependent stuff is here. And this is indeed the famous density operator. So that's one nice thing to think of, right? And then the rest of this, well, you get a resolution of the identity here, okay? So this is where you can actually start loosening up what you even assume the psi 1s were, okay? Anyway, so you substitute that, call this rho, call this the identity. And then what's left is you can actually take these bras and kets and contract them onto, since this identity doesn't do anything to the rho, contract these two onto the unitary on both the system and meter. Okay, so it's perfectly legal to then just chunk them like this. Okay. And now this is a new kind of object, the so-called Krauss operator. Okay, yeah. And so then in the advanced Born rule, this is called the Born rule, by the way. Some people don't like to call it that, or just never think to call it something. But this is indeed what Born was awarded the Nobel Prize for, is this interpretation of amplitudes. Yeah. The advanced way of quoting the Born rule is then just with considering sum over final states, average over initial states. This is how you would calculate things given a Krauss operator. Okay. Okay, so yeah, I guess I have a little bit of history here. So von Neumann is the guy who coined the term measuring process. He had something a little different in mind than what I'm calling the measuring process. To me, it's like when a measurement happens and it keeps happening, and at some point it terminates. There's a whole process to that. But von Neumann was just thinking about the outcome of that process, not having much to say about the process itself, just, you know, because operators are fantastic, whatever the process is, this is what comes out. Yeah, so like I was saying earlier, it took until 60s, 70s, and 80s for the real technology to be understood about what a generalized measurement is. And time is 403, great. Okay, and so then I label these two. These are textbooks, famous textbooks at the beginning of quantum information. And both of these guys like advanced measurement theory. And so I think they are the reason why anyone in this audience more or less knows something about what I'm talking about, if you know anything, or a little bit. Okay, so I guess I'll zoom in on this a little bit. So, you know, what this is saying is there's some state, like the electromagnetic field, and then there's some instrument that does something because of the electromagnetic field. Those could be things you hear, right? And then there's some state left over because this measurement happened, either because it had to siphon energy off of the field or other more subtle reasons. So I think this is a pretty intuitive way to just think. Yeah, you don't necessarily have eigenstates of a Hermitian operator. You have these more general kinds of objects. And if you really want to, you can always think of it as an indirect measurement. Okay. So there's nothing new. There's just a lot to understand about what kind of measurements you can do at this level. Any questions? Okay, so here's the lexicon. There's all kinds of words for advanced measurement theory. So of course, it's all about the Krauss operator. I hope that's pretty obvious just looking at this from a distance. So this is just a summary of things that I was showing in the last slide. One thing is just emphasizing that the cyclic property of the trace, right, means you can think of this as its own thing. And the set of these positive operators has its own special name. It's called a POVM, or a positive operator valued measure. Not very approachable term. So we just call it POVM and hope to remember what it actually stands for. Okay. So of course, it's the set that is the POVM. And the elements of the set you call POVM elements. So depending on who you are, right, there's this thing you call a super operator. So there's a notation called the O dot. Carl is a close collaborator of mine. He's thought a lot about instruments, and he's talked a lot to a famous guy about instruments. His name is Chris Fuchs. And Chris Fuchs gave him the repeated opinion that Carl should not use a tensor product here, but an O dot to emphasize that you're putting something there. Apparently, this is no longer his opinion, but he felt very passionate about it at the time. Yeah. So this is another little coincidence in this mystical image I'm giving you guys. There's an O dot on the forehead of this figure. So you should think about super operators. Good. So this super operator has a special name. It's called a selective operation, okay, or an instrument element, and because it's an element of this set of possible super operators or update rules. But I tend to be a little late or moody, depending on the mood I'm in. I'll either call the set of super operators or just the set of Krauss operators the instrument, because it's the X's which are what you're experiencing. And then you're just supposed to know what to do with these K's, right? Okay, but probably far more popular in the modern activities of quantum information is this super operator, the so-called non-selective operation, okay, or process. Okay. If you like pay attention to stuff that Sandia is doing, you hear about the process matrix. We're talking about this thing, okay, the sum over all outcomes. Okay, so of course, because all of this corresponds to probabilities and sampling probabilities, there's a particular condition left over on these Ks, which is this condition, the so-called completeness relation. Okay. Okay. So just to recapitulate, you could say an instrument is just a set of operators that satisfy this condition. In its purest sense, that's all advanced measurement theory is. Okay, but it's got so much richness to it. Yeah. Okay. And I guess another term I should say, because this is very popular, is to emphasize that if you are given this super operator, that does not uniquely define the instrument, right? There are actually many instruments that can so-called unravel the same overall super operator, okay? So depending on what you care about, yeah, you might be interested in this concept of unraveling. But I'm not interested in unraveling. I'm interested in specific instruments.
Is anything related to basis here?
Hmm?
When you unravel, is anything related to anything which you're choosing basis?
Yeah. In fact, the last time I was talking to Carl about this subtlety, Carl likes to call the measurement you do here the unraveling. So, you know, the meter has its own set of choices, right? How it interacts with the system, what you prepare the system in, and what kind of measurement you do sorry, what you prepare the meter in and what kind of measurement you do on the meter. And all of that makes different Ks, right? Okay, does that address your question? So regular notions of basis choice are in precisely these kinds of, cool. So usually I think of this X as an outcome of a position measurement because I like the real line. Okay, any other questions? Okay, so I could not have done all of this work without sort of groups holding my hand. So it's important to talk a little bit about groups. So Wigner, who's actually very famous for bringing groups to atomic physics, by the 60s, he wasn't thinking groups were that important specifically, but he was talking about how measurement theory wasn't finished. And it was because you really should know, have a more general idea of what it means to do measurements in succession, okay? And the von Neumann idea of measurement just doesn't know what this is, okay? To take the output of a partially measured system and measure it some more in a different way, etc. Okay? Yeah, so that's a thing that needs to be understood. Wigner pointed out to everybody in the 60s. Actually, I think people were already getting interested in it, and he just decided to put his 2 cents into it at the time. So now this is Lindblad's actual work in the 70s. His paper has the word semigroup in it. And I should emphasize the way I'm going to use groups is different from what he had in mind. For Lindblad, he was thinking about this total non-selective operation, okay? And he was just thinking about, well, if you do a continual measurement, so that there's such a thing as a weak measurement, and this dt, I'm thinking of it as infinitesimal, but it could have been finite. What kind of generators can you have of such measurements? And they have to be of this form, okay? And so then this L is the original Lindblad operator, okay? But something I want to emphasize is this took a lot of directions. Dissipator, by the way, was not Lindblad's term. A dissipator is a term that a lot of contemporaries use, and I like it. Okay, but this put things in a very specific direction, which is that people became obsessed about how states change when you measure them, okay? And in fact, this is what Lindblad was originally writing about. So there's this so-called Lindblad master equation, which is like the Schrodinger equation, except it also knows how the state changes if you measure it. Okay? And yeah, I should just emphasize this dominated the whole idea of quantum measurement for so long that I just have to say explicitly that's not what I'm doing. Okay. Okay, any questions? Okay, so because people have been obsessed about state evolution for so long, I wanted to make explicit this idea of the principle of instrument autonomy, okay? Which is instruments, measuring instruments are their own independent reality, okay? So the set of things that an instrument can do actually have its own distribution. So, you know, when you think quantum mechanically, you usually think there's a state causing these samples to happen. And that makes it very hard for you to walk away from these kinds of problems, because the state is causing the outcome. But I hope to convey to you guys that it's perfectly possible to analyze instruments as their own thing, okay? Principle of instrument autonomy. I am an instrument, I think I'm classical, and I am my own thing. Okay, so now a little misleading fashion. So a lot of the time, I think I've already done it a few times, I point at this and I call this the instrument. But of course, I'm talking about the set of things in that sum, okay? So like, if you do a lot of statistics and you like grand canonical ensemble or canonical ensemble, you do the same thing. You like point at the partition function and you're not actually talking about the sum except when you are. Usually you're emphasizing the things in the set. So similar fashion here. That's why I call this thing fancy Z, like a partition function. Okay, so I put in quotes here, right? It's very fashionable to just display the sum even though I'm talking about the set. Don't get confused. Okay, some examples. So this is, I think, the first really important physical example. So Davies is one of two independent sources of bringing measurement theory to the form it is today. And his setting ultimately ended up being in optics because having the laser and having all this radio technology, you could answer very interesting, you could ask very interesting questions in a concrete way. And I like to say, this work he did really is just this answering this question. What on earth is the effect of that thing, a photodetector on a quantum field? Okay. So yeah, in this case, the system is usually thought of as a cavity. So you've got some electromagnetic state bouncing around. And the meter is just empty space or the vacuum, maybe getting some energy and registering the photon or not. Okay. Yeah, so at small times, then there's two things that can happen. Either you don't see a photon or you do see a photon. And if you don't see a photon, this is the kind of Krauss operator you have, where A is the usual lowering operator. Okay. And if you do see a photon, this is the kind of operator you have. So something you should see is that it takes a photon out of the state of the system, which you'd expect, lowers everything. But then maybe what's surprising to most people is by positivity, even if you don't see something, the state changes. Yeah. Okay, so it turns out that, the statistics of these sort of 1-0 outcomes continues our Poisson process. So you can think of these Krauss operators as generating a Poisson process kind of instrument. Yeah, and this is the kind of statistics of rain. If you've ever heard rain, like that. So did I say everything that's on this slide? Yeah, so Davies had this much bigger picture of generalized measurement, and but it's with Srinivas. I tried finding a picture of Srinivas. I don't know what happened to him. I looked for him. I found many Srinivases. None of them were this Srinivas. Yeah. Nevertheless, I'm calling this the Srinivas-Davies instrument. Okay, so now here's another instrument. Okay, I call Wiseman's instrument, and this very much comes from his work. He didn't work with the principle of instrument autonomy. So if you ever read his thesis on this stuff, he's already talking about measuring a state by the time he gets to answering that question. But yeah, so this is just his work done using the principle of instrument autonomy. So his question, of course, was how on earth is that thing, the radio that's measuring photons? Very important question to ask. Nobody bothered to actually work out the math. He did. Thought it was an important problem. In that case, the Krauss operators actually, so here, what are you doing? You've got that cavity, it leaks, but you mix it with a so-called local oscillator, and you look at the difference of these two photocurrents. And then the output you get is now a classical random variable, it's not quantum, with a proportionality constant that is determined by the amplitude of the local oscillator. So there's this small continuum of outcomes you could get. And for each of those outcomes, so I'm pulling a fast one here, I'm sorry. There's this d omega, which is a very specific function of the dw that you read here. So I hope you'll just forgive me. That there's dw and then there's d omega, which is basically dw as far as this slide needs to talk about. And to each of them, you get a Krauss operator that looks like this. Okay, number operator piece. This is actually a Gaussian distribution with width dt. We'll talk more about that later. But what's important here is that all of these Krauss operators are close to the identity operator, which means they're not nearly as dramatic as the detection of a photon. And actually thinking of these as the fundamental building blocks to your measurement is not part of Wiseman's picture. Yeah, but to me, it's very meaningful because that's what's going to allow you to think about differential instruments, where anytime something happens, just a little bit of back action occurs. Okay. So, but part of Wiseman's work was indeed, if you do this kind of measurement, then you get the famous, by then famous coherent state measurement, resolution of the identity. Okay, so this is a nice famous result that heterodyne, what a radio actually does is intimately related with the coherent state resolution of the identity. Okay, so that was great. I mean, radio was invented at the same time as quantum mechanics, before quantum, the new quantum theory. And it took this long, what was that, 93, until people actually started to understand what it means for a radio to measure photons. Cool.
This alpha equals 2. The integral.
Yeah, so this alpha, the actual outcome is a very specific function of the differential process that you see. Yeah, just so that you translate. So there's some way to look at this, some cloud. Right? Yeah, and this is part of that cloud. Okay, any other questions or comments? All are welcome. Okay, so now I can introduce you to what I call differential instruments. So let's see, so let L be a Lindblad operator. You don't really need to know what Lindblad means. It's just any operator, really. Sorry, I lost my train of thought. Yeah, so, and you can interpret the, sorry, let me start over. So I'm going to consider meters that have outcomes on the real line. So I start the meter in the 0 state at the origin. And I can, if I interact that meter with the system, then I can either displace the meter or kick the meter. Okay. So kicking means it'll displace a moment later, but not just yet. Right. So this generator displaces the pointer. This generator boosts the pointer, and which the real and imaginary parts of this L tell you what they're doing. Okay, so the X is displacing and the Y is kicking. Okay, so then given that kind of meter, then you get an instrument like this. Okay, where this is.
I'm sorry, can I ask a question? This is Chris Moore from. I don't understand the distinction between displacing and kicking or displacing and boosting.
Okay, so Q is the position operator, and P is the momentum operator. Yeah.
Okay, thank you.
Yeah, so no. Displaces in momentum space, and yeah, okay. yeah, cool. And or you can think, yeah, P is just ddx and Q is multiplied by x. Yeah, if you want to sort of avoid saying it in a quantum way. Okay. Thank you. Let's see, where was I? Oh, so this this measure right here is the Wiener measure. Okay, so you've got these little, it sort of messes with your mind every time you write it for the first time. So dw is the variable, and it is a random variable with width dt. So it has its own distribution. So it's perfectly legitimate to write dw, but it takes some getting used to. Okay. So yeah, if you do this kind of measurement, then your Krauss operators look like this. Maybe you'll recognize this looks something like the Wiseman measurement, except L now could be anything, depending on what you're doing. Okay. And I find it useful to decompose it in this way. So if you write this in the real and imaginary parts, if you set the real part to 0, then that means this is 0 and this is 0. And all you're doing are random unitaries. And yeah, if this thing is Hermitian, so that this is 0 and this is 0, then you're doing these sort of multiplied by a Gaussian changes in your belief. Okay. And if you do both, then actually you get this interesting squeeze term. This interesting unitary. Yeah. Okay. Okay, so finally I can define for you guys what is a differential instrument. Well, a differential instrument is doing that kind of measurement previously over and over and over and over and over again, i.e. continually. Okay. So this is the same slide I showed you guys before, but maybe you guys have a better sense of it now. Okay. So if I do this, yeah, if I do this kind of measurement over and over and over again, that means I'm actually piling up these Krauss operators. Okay, so the first one, and then call it DW1, then KL DW2, et cetera, and you get these time-ordered exponents. Okay, so this is the same kind of Krauss operator for just a time dt as what I had previously, but now we're doing a bunch of them over and over again, and we might be doing a few of them, that's what this vector is, at the same time. Okay, so because they are weak at order dt, you can actually simultaneously measure all kinds of stuff, even if the observables don't commute. Okay, and I think I'll read this last line more carefully now, which is the Baker-Campbell-Hausdorff theorem means that this problem has almost nothing to do with the Hilbert space, i.e. it doesn't know what matrix it is, it doesn't need to, but rather is defined by classical differential geometry, which in this case means interpreting the Lie algebra of these observables you're given, these L's, as differential geometry. And the differential geometric way of interpreting a Lie algebra is the so-called push forward. Unfortunately, I'm not going to go over that with you guys. So maybe for now, you can just depend on, if I gave you a matrix for each of these L's, this is a problem you could do, either numerically or hopefully analytically. Yeah.
And without the matrix, if you gave us the commutator, right?
Yeah.
Yeah.
Yeah. Oh, yeah. Yeah. And you knew what the Baker-Campbell-Hausdorff theorem is, then you may not be able to visualize what these commutators are doing, but you could calculate. Yeah. Yeah. Okay. Questions? Okay, I've got 3 minutes, so let's see what I want to do.
Remember, we're going to take a break in the middle, and we're going to let people.
Yeah, well, I need to let people go. I can see some of you are tired. Yeah. So let me think for a moment about the last thing I want to say before I let people leave if they want to. Okay, so here's another breather slide. So I've been working on this project for almost 5 years. And definitely it's revived for me lately, thank God. But 6 months ago, this thing was like a dead horse. It was like, why won't you just be easy to communicate already? So this is a place I would retreat to over the summer. This is Hunter Creek. This is in the south side of Gold Beach. So this is where I was going to say, it's near here. So I would swim here. It's nice and cold. The rocks are nice and hot. It's a great way to temper myself because, I don't know, your nerves get pretty on fire when you do this deep kind of research. Ooh. So this has really been my healing spot for the afternoons, Hunter Creek. And so Carl's PhD advisor is Kip Thorne, who won the Nobel Prize in, I think, 2017. And he doesn't live very far from exactly this spot. And so I got to meet him for the second time just a few days ago talking about Wigner, and because I'm a big fan of Wigner. Yeah, it's trippy. Who would know? Okay. Okay, so now I'm going to apply the entire differential instrument program to the simultaneous measurement of Q and P, and show you guys what that looks like. There's actually two layers of what that looks like. If you know Kolmogorov theory at all, there's distribution functions, and then there's stochastic equations. So the next part of the talk is what are the stochastic equations and the 7-dimensional manifold for simultaneous QP measurement. And then the section after that is what is the density, okay? And then the section after that is more philosophy and bigger picture, what this all means, okay? So I guess I should just keep going. Yeah, so it's 4:30 if you have somewhere to be.
I think this is a good. I think this is a good pausing point to say.
Oh yeah, intermission.
Like, let's do a tiny intermission, and then jump into the stochastic equation.
Sounds good to me.
That sounds good. Yeah. Okay. So we'll take like a couple minutes, leave if you need to. Use the restroom.
Great.
Then come back in 3 minutes.
Great. Thank you.
Yeah. Absolutely.
Thank you guys for coming. If you decide to go, see you in a couple minutes. 3 minutes.
3 minutes. 180 seconds.
Here we go.
I know, I'm so excited. It's gonna be so good. This is already fantastic, by the way.
Have a problem.
Huh?
The people can't see what is Chris pointing. Presentation with the tree.
So let's orient your camera.
No, there is an option to use the mouse like a point, like a laser pointer.
Oh, but that would mean
I
I have to stare at my screen.
Yeah,
And yeah, I would rather, sorry.
Yeah. This will work okay.
Okay.
Let me look at the chat real quick to see if anyone was. Oh. Marco, how are you doing? Yeah.
I arrived 3 weeks ago.
Oh, where'd you go?
Huh?
Where'd you go?
No, three weeks ago I arrived.
You arrived.
Yeah.
Yeah, where did you go?
I'm from Mexico.
Oh, you were here like so you're like a postdoc now?
Yes.
I see. I'm like, we're here the whole time. Cool.
Yeah. Marco and Bruno are newest postdocs.
Bruno?
Bruno back there.
Bruno?
There's Bruno, Marco, our new postdocs. And then are all the other postdocs missing? Yeah, that's right. That's okay. You'll meet them one day.
A little bit. If you want to meet on Monday, I'm supposed to meet postdocs on Monday. I have to leave at 10 o'clock. So how early do you guys wake up?
Hey, Chris, I have a question in the chat.
Oh, hello. John DeBrota.
Sorry, I can't really talk much. I'm at the airport, but I wrote a question.
Oh, that's so nice of you. I've lost track of where the 7-dimensional manifold is. Indeed, so I haven't actually talked about the coherent measuring processes just yet. Those are where the actual 7-dimensional manifold is. So for now, I've just been saying 7-dimensional manifold. Yeah, so you don't know where it is yet. Yeah, good, good. I'm just anticipating it heavily. Cool. Oh yeah, so Monday. If you guys want to meet, I think I'll show up at 8 o'clock, and whoever shows up, we can chat. But I have to leave at 10. And if you could spread the word, because not all the postdocs are here. If you're not a postdoc, you can come too. Actually, assuming that's okay with. Yeah, all these postdocs are friendly.
8 a.m. You said?
Yeah, let's just I'll show up at 8 a.m.
Sounds good.
I do. I have to check into a badging office in Los Alamos at 1 o'clock, and yeah.
Don't take photos. I learned that. No matter how funny the posters are, the posters that tell you not to take photos are the funniest posters in the world. But you can't take photos.
No,
of them.
yeah. I don't think I would have been tempted.
So did you get a badge on that?
I did.
At the badging on?
And I returned it.
Oh, I know you should return it.
Yeah, I know you know that.
And that was a pleasant experience.
I wouldn't go that far, but they give you a 45-minute window. You do not have to show up exactly on time. It at least was an experience that happened.
Yes, well, that's all it counts.
It must have been classical.
Yeah.
Cool. Are we ready?
Yeah.
Okay. Thank you guys for staying. So now we're going to start talking about 7-dimensional manifolds. Yeah, let's see. What do I have here? Okay, so there are 4 problems that I can solve with all of this technology I've started hinting at that I think are very important, okay? They're what I call the 4 legs. Okay, so the 4 legs are what this square in this guy's chest is referring to. Okay, 2 of them are spin measurements, and 2 of them are amplitude measurements. Okay, I give the amplitude measurements the names of these guys I've been showing you pictures of earlier. So there's the Wiseman measurement, which has to do with heterodyne as it was originally modeled. It's actually an approximation of heterodyne. But then there's this other simultaneous QP measurement, which is important. It's not exactly like just removing rotating wave approximation, but it has a lot of the technical details you would have to deal with if you didn't do this approximation, okay? So this guy Barchielli, who gave a shot at this problem back in '82, could not process what on earth these cross operators were doing nearly as much as I've managed to, but he was the first to think about it. So yeah, I'm going to name this instrument after him. And this is going to be the dominant topic of this talk. Okay, so things on the left are amplitude measurements. Things on the right are spin measurements. Things on the top assume a conservative system meter interaction, which turns out to do plenty of wonderful group theoretic things. Keyword is Borel subgroup if you like group theory. Okay, so, and then on the bottom, yeah, you get this genuine 7-dimensional evolution.
So the bottom is the more general case.
It's not general, it's different.
Okay.
Yeah. Yeah. The bottom is just a different system meter interaction. Yeah. Yeah. Okay, so if you guys knew me a little bit when I was here a few years ago, this corner is the one that I discovered with Izad and Ivan and a couple other guys. Okay, so on the bottom right. The one on the top right, now that I actually understand heterodyne a little bit, became clear. And who knows if I'll ever have the time to write on that, but maybe someone might want to pick up that project. Okay, but the 4 corners, great, or 4 legs. Keep calling them 4 corners. I like to call them legs because they are what give this work legs. Otherwise, it looks a little too abstract. So there we go. Okay. So yeah, like I was telling you guys, this is the instrument I'm going to be talking in depth about. Give you a sense of what this differential instrument program looks like. Okay, where do the 7 dimensions come from? So if you know Baker-Campbell-Hausdorff, it means that if you start doing this kind of piling up problem, then what you have to worry about are lead brackets, okay? So to first order, you start generating motion in these 3 directions. I'm going to call them velocities, just to be geometric about it. Velocities in some space I haven't quite specified yet. And then the second order terms, to second order, you actually start going in new directions. Okay, what I'm calling I omega. You can think of omega as just 1, if you like. It commutes with everything. I haven't made up my mind about where to put H bar, so if you're looking really carefully at my equations, you might notice the H bar choices are not consistent, so please forgive me. Yeah, and then so you step in these 3 new directions. And then to third order, you start stepping back into these directions again. They're not new. But then there's the seventh direction, okay? So it's really important that I, Q, and Q are different directions. I'm counting real dimensions, okay? And they do very different things operationally or physically. And then I'm asking you guys to trust me that to fourth order, there aren't new things. Okay, so there's 1, 2, 3, 4, 5, 6, 7 dimensions. Okay, so that's how you first know at a local level that this problem is about motion in a 7-dimensional manifold. What's that?
Is this torsion there?
Yeah.
Is that torsion as in the binormal vector or the trajectory?
Yeah. In fact, so binormal, if you're using Clifford algebras, right? This is an anti-commutative object, right? And but I thought you said bivector, excuse me. You said binormal. I'd have to think about that. I haven't thought about, so binormal is a notion that's defined only in 3 dimensions,
Yeah.
right? And it probably is related to this. I just haven't thought about 3 dimensions in a while. So, yeah.
Scale, like more dimensions.
Yeah, so this might be the generalization of the binormal vector. I'm willing to guess that, okay? Yeah, because the cross product doesn't, the Lie bracket is a kind of generalization of the cross product. And I guess the binormal is defined as the tangent and the normal cross product. And so in that case, yes, I'm even more willing to guess that indeed this is a generalization. So this is a multidimensional generalization of the cross product. Depending on what you want from the cross product, if you're thinking about wedge products as generalizations, I mean, don't attack me. Okay, but this is an antisymmetric object that generates new directions in a meaningful way. Okay. It just so happens that there's other orthogonal directions you could go in besides just the last one. Okay, yeah, true. Okay, 7 dimensions, there you go. So you got your 7 dimensions, good. All right, so I'm not going to do my differential geometry in a Riemannian fashion, which is to define connections, etc. I'm going to take sort of a cheat route. Okay. One, well, I think the most important reason why is because it turns out the 7-dimensional manifold isn't Riemannian. It always tripped me out because, you know, when you visualize geometries, you're like, that's the distance. What do you mean there are non-Riemannian manifolds out there? But this is one of them. So take that. Okay, so, but there is this wonderful geometer from the early 1900s, Elie Cartan. So maybe you guys have heard about the Euler decomposition. So Cartan understood, and maybe Euler did too, I don't know, how the Euler decomposition, so like KAK could be Z rotation, Y rotation, Z rotation. He understood how multiplying these guys is the same thing as moving around the 2 dimensions of a sphere. So the polar angle would be the A, and the azimuthal angle would be, say, the K on the right. And that the K on the left is actually the holonomy. So, you know, we live on a sphere. We're actually going east as we speak, as I speak. And if I was standing on a frictionless turntable for a while, and this talk went on for a couple hours, you'd actually notice I'm slowly turning to the right. Yeah. And so that's a local angle, which is actually what this K on the left is. Okay. And so the group SU2 you can think of as what's called the frame bundle of the 2 sphere. There's this whole world of geometry there to appreciate. Okay, so that's one angle to think about these things. But maybe if you're a quantum physicist especially, you're more familiar with things like singular value decompositions. So singular value decompositions are actually the same, they're representations of Cartan decompositions. But what's important here is that what's being described are paths, not matrices. So you might say, well, A could be represented by a matrix of singular values, but the singular values are not the point. It's the way that these dimensions are connected to each other that is the point of the Cartan decomposition. Okay? Just give you a flavor. So if I said this in a more standard way, so all of your cross operators, you start piling them up, right? So this is some K you might get from a differential process. It's always going to be of this form. So I'm doing both spin and amplitude. So you have a displacement operator in a phase space, either a sphere or a plane, okay, in the past and in the future, okay, because the state is something you act on to the right. And then what you get left sort of goes through the cross operator on the left. And then there are these three parameters, which are the geodesic curvature. So you may not go on a straight line from n hat to m hat. And so you get this factor. And then these things I've been calling the renormalization factor and the collapse factor, or the inverse temperature-like parameter. Okay. Okay. So let's see, what else is important to say here? So you might realize that this is already true just by acknowledging the singular value decomposition. This is just saying there's something positive and diagonal, times a unitary on the right and a unitary on the left. But again, the important thing is that these 7 dimensions don't have to do with quantization. Okay? Okay. It's not about the matrices. So I like to say the singular value decomposition is a representation of some Cartan decomposition. Okay. Okay. So great. If you study a little bit about Cartan decompositions, usually they're thought of in the context of semi-simple groups. That's when this manifold actually is Riemannian, which is what Cartan was originally considering. So technically calling this amplitude analog a Cartan decomposition is, there are authorities who would probably bite my head off if they heard me say it. But so I'm calling it Cartan. Maybe I should call it Cartan-like. So here I have in parentheses, still morally semi-simple. There's all kinds of topological details that you could hit me in the face with, but all of this stuff is right, so yeah. Okay. Great. So 4 of these dimensions actually affect the POVM. POVMs are meaningful to you. And then 3 of these dimensions are just what the post-measurement state is, and they are more dimensions. Okay. So here we go. I guess I'm not going to show you guys how you calculate these because there's just so much to talk about. But if you understand Maurer-Cartan forms a little bit, then you can get from this time-ordered exponential problem to these 7 SDEs. Okay, so this is the quantization-independent motion in a 7-dimensional manifold that I've been telling you guys about. Okay. This is 7 equations because the second and third one are complex. Okay. I know you see 1, 2, 3, 4, 5. I'm not trying to mess with you. These 2 are complex. Yeah. Okay, and actually the solution is complex too. Right? No.
The last one with the omega.
Yeah. What do you think is complex?
Oh, sorry, I forgot the process. Yeah.
Sula's been exposed to this work before, and I used to call this thing omega.
Yeah. Okay. Yeah. We're good.
Hey, Chris, could you sort of tell me again why it's quantization independent? I don't really get that part.
Yeah. So what I mean by quantization is replacing the observable with a matrix. Okay. And what is the matrix corresponding to H naught? What is the matrix corresponding to Q? Has nothing to do with those SDEs.
Okay, I see.
Okay. Yeah. Okay. So 5 of these dimensions are very easy to solve for, and they look like this, and they make a lot of sense. So this is what Austin was getting at, that this dimension, which is like an inverse temperature, because it's in front of this energy-looking quadratic term. This isn't really an energy, right? It just comes from the positivity of the measurement. We're not doing statistics, but it's the same operator ultimately. Yeah, it as this time. It evolves trivially in time, or directly in time, linearly in time, that's the term. Okay. This future parameter, in fact, depends on the measurement record in this way. And what you should see here is, oh no, I'm so sorry, on the beta, on the top right, this is supposed to be cosh 2 omega kappa little t. Okay. So sorry. So if that's little t, then you can see that this thing is order 1 for little t on the order of big T, and is exponentially small for little t small. So that means beta only cares about the end of the record, while alpha only depends on the beginning of the record. There's this sort of decay behavior. And that makes a lot of sense if you think about it. Okay. These last 2 dimensions are tricky. And I'm still in the middle of working out what they're doing. But I am the most interested in this L parameter because this L parameter doesn't actually change probabilities or updates. It doesn't really do anything to the state. Nevertheless, it is something different that the quantum physicist does when they divide by the number to renormalize their state. They need to know what this number is to renormalize the state. So this sort of like, you can't really remove the physicist because he has to know this, but the Hilbert space could care less. The state evolution could care less about this parameter. Very subtle parameter. I can't help but think it's exactly why renormalization group is a thing. It's because these kinds of fields are subtle. Measuring them is subtle, and the scale of things and changing, oh my God. But I don't understand it fully yet. Yeah.
But you said it has nothing to do with like probabilities to observe particular outcomes.
Yeah, these STEs. Right. But when you do quantize, right, the probability of these 7 dimensions having a particular value is according to the Born rule, right? Because you use this Krauss operator, etc. Right? But this time evolution of the Krauss operators is its own thing.
Yeah.
Right. Yeah. But in the end, if you actually sample, a state does cause that sample. Right? There's just this more abstract evolution that has nothing to do with the state. Yeah. But of course, real sampling comes from states. Okay. Did I address your?
Yeah.
Any other questions or comments? Okay. So this was going to be the original last slide before I let you guys go. So back in 2018, this is when I, with Ivan and Azad, published the first paper on simultaneous measurement of spin components. I was very unhappy because all we did was SDEs. We didn't even process it as much as the kind of stuff I just showed you. We just said, oh my God, time ordered exponential. Oh my God, Cartan decomposition. Oh my God, oh my God. And so it was the equivalent of more or less processing the SDEs. But I knew from Kolmogorov theory that, well, we should be able to do this problem by talking about some density, some distribution that's diffusing, okay? So this whole idea that you can analyze stochastic systems and also quantum systems in an analogous way in 3 different ways, either considering path integrals or stochastic differential equations or density diffusion, is what I'm calling the Trinity, okay? And I did not understand how to do this in 2018. So when I would see Carl in the hallways, he'd ask me how I'm doing, and I'd tell him I'm trying to understand the stochastic Trinity. Yeah, so that's what this thing in the corner is about. Okay. Okay, and so then regular stochastic Trinity for like real variables fluctuating, no curved spacetimes, manifolds. I'm calling the Kolmogorov Trinity. I think that's fair. And then the fact that, you know, a Schrodinger wave function can be thought of as a path integral. And I guess there's some kind of STE way of thinking of that whole thing too, if you know how to Wick rotate. Maybe it's what the lattice gauge theory guys do when they simulate. I don't really know. I'm calling that whole thing the Feynman trinity. Okay, so there's a whole trinity for instruments as well. Oh, so yeah, this was the original summary. So I'll give you guys the summary now, and then this will finish. Oh, I'll just tell you what's on this slide, excuse me. Okay, so this is all the stuff that was on the beginning. The principle of instrument autonomy is a totally different way of thinking about what something like the canonical Weyl-Heisenberg algebra is even talking about. What I'm talking to you guys about are these differential instruments. Their raw outputs are these Wiener processes, and from the context of the observables you're measuring, there actually is some manifold that those Wiener processes live in. You just got to know how to read them. And I showed you guys these 7 very specific SDEs. That is the cloud, right? Okay. Yeah, and the only reason why I can get those SDEs is because I have a Cartan decomposition to work with, okay, a coordinate system for this manifold. Okay, and then these last pieces are teasers, and then we'll have like another little intermission maybe. So indeed, you can do evolution of what I call the Krauss operator density, okay? And wonderfully, even like I said, none of this has to do with quantization. Don't need any matrices. These are just changing, moving in places in this abstract 7-dimensional manifold. Still, the Planck distribution comes out. But the Planck distribution doesn't come out from quantization. It comes out from the completeness relation. You guys remember sum over k dagger k is equals 1? Well, the way that this distribution actually behaves gives you exactly this factor. And then with Schur's lemma, you know that this thing is just the trace of the thing in the middle. And you recover the same result as if you quantize the energy. Okay, so this is to be expected. There's what's called the Stone-von Neumann theorem, which says morally there's only one way to quantize. So not quantizing basically is quantizing because there's only one way to quantize. But the story here is different, right? Because I'm not talking about temperatures and states and energies. I'm talking about a measurement, and I'm talking about the positivity, just the positivity of sampling and how that affects the way this instrument evolves. And so this 2 sinh 2 kappa t, which is 1 over the trace of that, is actually, excuse me, sorry, is actually more describing the space of the size of these phase spaces as R evolves. Okay, so it's a feature in this manifold. Okay. So that's cool. Energy quantization is the same thing as this feature in this manifold. Yeah, so it's just another way of getting at the whole operator algebra. That's the way I like, because I think I'm more of an instrument than a quantum state. Yeah. Okay, so that was the original ending. So I'll give you guys the acknowledgements, and then there's another phase of this if you guys want to hear about the Krauss operator density. So I'd like to thank Mohan Saravar. I'm currently employed by Sandia National Labs in California, but I've been working remotely. Yeah, Mohan found me sort of serendipitously before I ended up not going to Australia as originally planned because of the pandemic and all kinds of complexity. Yeah, so Mohan scooped me up, gave me a job, and my job is almost over in like 3 months because I chose this project over job security. But of course, big acknowledgements go to Carl, who is the guy who's been paying attention to me for the last 2 years, keeping this project alive. Yeah, those are my 2 acknowledgements. Oh, and of course, whoever the money actually came from, grant DENA 0003525. Okay. But last but not least, I'd like to thank all of you guys for your attention. Yeah. So, maybe we should have another 3-minute intermission. I'll give you guys another nature slide to look at. So this is the northern part of Gold Beach. From the house of my friend. I'm living in her house. Friends are good.
All right, so I'm going to poke you during this intermission with a question.
Okay.
You know, sure, the Planck distribution has come out, but you have already specified the commutation relations. I mean, yes, you haven't assigned them a matrix interpretation,
yeah,
but you still have, you know, prescribed the Lie algebra.
Right.
And
yeah. So
you
it's
know,
not
if,
different.
and if I was like, you know, a really young quantum physics person, I'd be like, well, isn't that just already prescribing the quantum theory?
Yeah, and it is, right? But historically, so, you know, Planck quantized the energy, had no idea why that was the right thing to do. It just got the answer right. And then it wasn't until wave particle duality happened that you realized that ddx on square integrable functions is what's going on. And therefore the actual interpretation of these ladder operators acting on a basis, etc., happened, right? So this whole thinking about thermodynamics or statistics and thinking about energies is just different, right? So we're not thinking about statistics and energies. We're not quantizing energy. So the same algebra is there because it's uniquely defined by the Lie algebra. It's not uniquely defined in the spin case, but it is more or less uniquely defined in the amplitude case. So it's just a totally different perspective. That's all. With the same operator algebra.
Can I ask you a question before I leave?
Yes, please.
Yeah, so I wanted to ask, yeah, something that I was kind of hoping to see in the previous slide, because I don't have a whole lot of intuition about continuous measurement.
Okay.
One question that I had rolling around the back of my head about this continuously measuring non-commuting observables. Okay, if I weekly measure commuting observables over a long period of time, I can get a sharp projected.
Yeah.
Right?
Yeah.
And sharp projected measurements always seem to increase the purity of the quantum state. Right. So yeah. Kind of, it's a question about how does the quantum state respond?
Absolutely.
Does the same hold for?
Yes, it does. So absolutely. Fantastic question. So if you quantize, so this H naught, okay, this e to the minus, remember R goes like time. So this becomes a projector onto vacuum. And it increases in purity.
Okay.
Yeah. So in fact, that's how, because this becomes a projector onto vacuum, then this acting on vacuum on the right is a coherent state. And this acting on the left is another coherent state. And it recovers the second slide I was talking about coherent state measurements as a motivation. So these in fact implement coherent state measurements. Yeah. So does that answer your question? This is indeed where the purity, sometimes I call R a purity, right? Because this thing is becoming purer and purer as R increases. Yeah. Great question, indeed. Yeah. Very different idea of collapse.
Yes.
We're not
talking. I
talking.
guess since it pushes me to a coherent state, I can kind of think of the state that I get to at the end is containing some information about the dot.
So it turns out for this measurement, remember, oh, these are great questions. Thank you. Remember these formulas?
Yeah.
So this actually only depends on the end of the record. Well, this only depends on the beginning of the record. So they're like these exponentials with a depth 1 over the measurement rate. And when the measurement has happened for long enough, actually there is no correlation between the post-measurement state and the output, the POVM output. Yeah, so they become uncorrelated. Yeah.
So the POVM is
yeah, exactly. Of the beginning of the record.
Yeah.
Yeah. And then the end of the record, you're just measuring something else at some point. Yeah. Good to see you.
Great talk.
Yeah, thank you. Okay. Wow. So for the diehards, here we go. Whew. Okay, so we're about to accomplish the Trinity, which means that we are going to know how to think about this problem from the perspective of diffusion processes. So Carl's probably spinning right now because this word universal, I used to say principle, because there's two kinds of group theoretic concepts out there that are related to this work. There's this idea of principal bundles. There's this idea of universal covers. And yeah, Carl and I have been understanding universal covers a lot better lately. And it just feels more appropriate to call this universal now instead of principal. But yeah, so sorry for the spinning. Every time you see universal, it says principal. Yeah. Okay, so here's the key. So you've got this motion in the 7-dimensional manifold. That 7-dimensional manifold is a group. I don't call it a group because physicists have all kinds of things in mind when they hear the word group that I don't think are helpful for this, but maybe they are. But that group has a Haar measure. Okay. Did I put it here? It'll be on a slide soon. But that group has a Haar measure. And it also has, because of the Haar measure, a delta function. Okay. So what does the delta function do? It just, reacts dramatically to when these two arguments match. Okay. So you might have, if you've been paying attention, this is not a K anymore, it's a gamma because I'm changing my perspective a little bit. So I'm pointing out that, if you started out with the Krauss operator, you probably had a Hilbert space in mind. And the fact is, because the Baker-Campbell-Hausdorff doesn't care about matrices, that Krauss operator always factors into two terms, okay? A term that goes into the so-called universal cover, this manifold that exists independent of the quantization. But then there is the representation of that manifold in the original operator space, okay? So breaking up the Krauss operator into a representation of some principal or universal trajectory. Even I'm still calling it principal. I'm so sorry. Yeah. Okay, so same problem we had before. So this is me just reminding you guys. Oh, I probably didn't say this out loud, but this K O dot K dagger, I'm now just calling fancy O of K because, oh God, that's supposed to be a, oh no, that's right. So fancy O of this whole thing, right? I don't want to write this whole thing, O dot, that whole thing, dagger. Okay. Sum over Wiener paths. So if you plug this into that, then you can put together all of the Krauss, all of the Wiener paths that give you the same Krauss operator. Okay, that's all we're doing. So in that case, we have sum over possible values of the Krauss operator, the selective operation, times this new object that I call the Krauss operator density. So this is a kind of representation, has a special name as of 1966, thanks to Harish-Chandra. It's called a tempered representation. So this is a nice distribution, so it's a tempered function. These are representation, tempered representation. This is not the 2 plus epsilon's integrability of Harish-Chandra's original definition, but I think they're equivalent. So that's what this word temperance really is about, is the theory of tempered functions, tempered distribution, tempered representations, excuse me. Okay, and when you think, in this case, the Krauss operator density is just a sum over all paths that give you the same value of x. Yeah, great. This thing on the bottom is a little story. So Haar published on the Haar measure back in 1933. Apparently, when he published this paper, it surprised von Neumann. And so this famous von Neumann surprise I thought was worth mentioning here because it kind of shows that von Neumann wasn't thinking about things quite like I'm thinking about them, right? Yeah, so much had to happen over the next few decades to even have the possibility of this perspective. Yeah, so things kind of missed each other. Yeah. There's this term locally compact topological groups. This was before stochastic differential equations were invented. So people had their own way of thinking about what finite amounts of information, but not differentiable, could even mean. So this was a way of thinking about what finite amounts of information, but not differentiable. It's a way of thinking. If you've ever taken like a point set topology class, you know, these guys are obsessed with limits and open sets. And, you know, this was during that time. Yeah. Different ideas of connectedness or separability. Wow. Okay. So here again is the definition of the Krauss operator density as a sum over measurement records that give the same Krauss operator. And you can think of this as a Feynman-Kac formula to some diffusion equation. Okay, so Feynman-Kac formulas are path integral expressions to diffusion equations. So there's your path integral. But I didn't tell you what the diffusion equation is, so I'm trying to get to that. So here is the piling up of the Krauss operator problem again. I'm giving this term that comes from positivity its own name, call it V of L. Okay, so that's just a restatement of what a differential instrument is, thinking of it as a sample path. And sure enough, you can just read off of this what the diffusion equation is. So this thing corresponds to a first order derivative, which generates displacements. And these stochastic terms actually correspond to second order derivatives. Okay.
How do we see that read off?
Here's an L. So this I can write as Li dwi. And for every dwi, I get a second derivative in Li. Yeah. And a half because of the Taylor series.
Okay.
And similarly, this thing, when I expand, it's just a first order derivative. Okay.
Yeah, I guess it's a little puzzling just because you see, you look at the positivity drift, you see pairs of L's, and you see up here, you get the one L. But
no, I'm using slightly different notation. I'm sorry. Here, this is vector L dot.
Yes.
DW. So that's actually a list of L's.
A list of L's, but still a list with one L in each term, where this, I don't know, I was a little puzzled by how the L squareds here go to first order derivative.
Oh, so this is one big term.
Yeah.
And so it is just one big drift.
Yes.
But these DWs are independent. And so they give different squares.
Yeah.
So if this was just one, if this was the sum of the L's and this was one Wiener increment, then you get the sum squared. Right. But you get independently squared because each of them has their own Wiener increment.
Yeah.
Okay. So really, I'm just pointing at symbols because it might not be obvious to you at all how on earth these are derivatives. So they're a new kind of derivative. They're called right invariant derivatives. They're a technology I had to learn because this is a fundamentally right invariant process, right? When more information happens from your measurement, you just put more stuff on the left. So then whatever's on the right just has nothing to do with anything. But even though that looks trivial, as far as the 7-dimensional geometry is concerned, this actually is a profound thing that you can differentiate in this space in a way that's more twisty versus coordinated. Okay. But in the end, if you actually want to solve something like this, you have to go back to coordinates. So now we're back at the Barchielli instrument. Okay, simultaneous measurement of Q and P. If I write this generator of the Krauss operator density evolution in these coordinates, I get this thing on the right. And I don't know about you guys, but first time I looked at this, I was pretty intimidated because, well, this term looks easy to handle. This term is easy to handle. This term is easy to handle because they keep Gaussian as Gaussian. But then you've got these kinds of terms. You've got a coordinate times a derivative and another derivative. So this is like a cubic term. And you get this quartic looking term. Oh God, And of course, the first time I looked at this, I didn't write it as nicely. It's just this mess that's drowning it. But that is the equation, okay? A lot of interesting stuff to see in there. So these del i's are a kind of derivative. This 1/sinh is like, the 1 sine theta in spherical spaces, spherical coordinates. And this cosh is like that rotating effect I was talking to you guys about. Yeah, and there's all, this is actually even messier if I keep the dd psi terms around. So I'm just trying to give you something. Actually, this is still accurate, but this has another term in it, which is what this mod means. There's the Haar measure in these coordinates, something to look at. And it turns out that the completeness relation for this density translates to a symmetry that the density has to satisfy. And that symmetry, which is conjugating by unitary displacements, that symmetry translates to differential conditions on the density. So that's something that supplements the Kolmogorov problem. Kolmogorov doesn't know you're talking about instruments, but in this problem, there's extra constraints on your distribution. Okay, so now for something to show you guys so that we can get to Planck, which is if you go back to the instrument, you can separate the Haar measure into 5 and 2 dimensions. So this is me plucking out the d psi dl piece, okay? And taking out all of the L and psi dependent bits in O. So actually the psi doesn't make it. The psi is a symmetry of the instrument element. The L makes it. So you look at this and you say, okay, so I have some good sense of what the instrument is doing if I instead had this function, the CT of ZX. And indeed that guy, so all of those nasty cubic and quartic terms go away for CT. And so instead you're left with this differential equation, which with the symmetries, the second derivatives look a little different. And that has a pretty easy solution, okay? This is again what I was saying earlier, that the purity dimension just moves ballistically in time. So this density just sort of moves ballistically, this front, this 6-dimensional front. But then alpha and beta become uncorrelated in time according to this sigma factor. Okay, so this thing is cubic for small times and then linear for long times in time. And then this crazy term, this 2 omega over sinh omega r, which comes from this piece of the forward generator, this coth. And yeah, so the Haar measure had a sinh squared in it. And this has a 1/sinh in it, actually a 2/sinh. And so indeed sinh squared, there's 2/sinh, 2sinh. Yeah. What's up?
So would you say there's like 6 dimensions?
There's a 6-dimensional front. So it's 1 dimension is being moved through. So like in a plane, if a plane was moving like this, I'd call that a 2-dimensional front moving ballistically in this 1 dimension.
Okay. Okay.
Cool. All right, one more slide, and then we can talk philosophy if you guys want.
Well, okay, let's back. Well, is it obvious to see positivity is concerned already?
No. So one more slide. Okay.
Sorry.
Okay, so here's me again saying you get a sinh squared in the rest of the Haar measure. Then you get this 2/sinh in the actual solution of your Krauss operator density. And if you apply completeness, right, you get this factor. Okay. So this beta, this whole Gaussian disappears because the integral over beta just absorbs things. And so actually the alpha dependence completely falls out. And so you're left with this. And by Schur's lemma, indeed, that is the trace. And you get the famous result you would get if you instead quantize the energy. And here I am emphasizing again that I'm not talking about temperature and energy of the thermal state. Okay? We're talking, this is literal time. And this is coming from the positivity of the instrument. And this is an instrument. This is a measuring instrument. We're not talking about states. That's cool. I'm very into that idea. Okay. So that ends the technical bits of the topic. Okay. Now there's like 5 more slides of philosophy, von Neumann, and yeah. Check this out. So this is, if you drive to Santa Fe and you look to the right, you're going to see this mountain. And I love this mountain because it looks like a Lorentzian. I mean, look at it. I mean, that is the most perfect Lorentzian I have ever seen. And I don't know why it looks like a Lorentzian. I have no idea. I mean, I have no idea. Yeah. You can't think about Gauss's law in the obvious way and argue that that should be right. This thing is being pushed, it's not being pulled taut. Okay.
The last slide real quick.
Okay. Yeah, of course. I can also email these to you. Yeah. Would you shoot me an email so I can remember?
Yeah.
Oh, right. So a few more slides, reflections and future. So I'm going to go through all of the symbolism again, just in case it wasn't obvious. So the O dot is because, well, I use O dot for instruments because Carl used O dot because Chris Hooks told him to. But also, you know, the sun has always been a symbol of autonomy. So I like to use it to also symbolize the principle of instrument autonomy. Okay. Then there's this thing in the middle. It's called the septenary. I'm not a theologist, but this is a symbol from them. But it's a triangle and a square. It's got 7 corners. And so I think of it as applying the instrument trinity to the 4 legs. Okay. Triangle on the square, but also it's got 7 corners. And so, you know, all of the 4 legs are these 7-dimensional manifolds. Great. These 2 irises, I decided to make them my offerings to Wiseman and Barchielli. You know, they did some really nice work and I really appreciate what they did. And I hope I'll get to talk to them someday about this stuff and they won't hate me for it. Oh, good. Those academics, you never know. Okay, and then the 2 wings I think of as the 2 Ks in the Cartan decomposition, which are actually what gave this whole program flight. Without the Cartan decomposition, I couldn't have understood these 7 dimensions. Cartan decomposition is what defines those 7 dimensions. And it's just like really fancy polar coordinates. Yeah. A few more symbols. So then these cups with the flowing water. One of them I already told you was it's like the future and the past 2D phase spaces with these 3 1-parameter subgroups. But the original thing I saw when I looked at this symbol was the so-called reading tea leaves, right? And that's what the cloud was. You look at the Wiener processes, these squiggly looking things, they look like tea leaves to me. You look at them and you somehow know what they mean, okay? And that's what the SDEs were that I showed you guys, okay? So yeah, just the fact that this is a cup with some squiggly thing, right? It's like reading tea leaves. Okay. And then the word temperance, like I was telling you guys, is in reference to the tempered representation, okay, which was a very important feature of thinking about the measuring instrument in terms of the Krauss operator density. And then finally, there's the path to the crown. Okay, so the path is supposed to remind you of sample paths and this whole sample path diffusion correspondence. Okay, and the crown is, I guess, accomplishing the Trinity, knowing how to think about this instrument literally as the Kolmogorov evolution of the Krauss operator density. Yeah, so that's the symbol. The temperance card is a very famous symbol, so you can Google it, look at it, see if you remember anything about what I just told you. Okay, so the point of this slide is to talk a little bit more about groups and what physicists think of when you talk about groups. So, most of what physicists think about groups originates out of these ideas of Wigner and Weil. So a lot of physicists will say, what is a group for? A group is for describing symmetry. And these days, what that means is doing representation theory, which usually means making field theories, okay? But this is not really how I'm applying. I mean, I am talking about amplitude and spin, which could be in fields.
You have a nice O dot right on your forehead. When you turn back, it was great.
Yeah, but this principle of symmetry wasn't exactly helpful for thinking about this Krauss operator density and Cartan decompositions. Okay. A term that Weil liked to use, which I thought was very good, is this idea of virtual motion. I don't know if it's his term or if it's Klein's term, but when you talk about a phase space as a place where there's all these places you could go, and you use this group to unfold all of the sophisticated mathematics, there you are using virtual motion. It's like you've got this geometry, and how do you even understand the geometry? Because you can move around it, but that motion isn't dynamics. You're not talking about things being generated in time. You just could move if you wanted to. You move around enough in your mind until you get it. And yeah, so virtual motion, in a sense, I think Einstein probably would have argued with this, but he knew how to change velocity in his mind and think about space-time. So he had accomplished virtual motion of the Lorentz group, right? Yeah, but virtual motion is also how you move around phase spaces. And this is how these two guys, Brelamov and Gilmore, originally thought of coherent states. Right? I was just talking about like the sphere, plane, Wigner functions. And even Hilbert space has a kind of virtual motion because you move around it with unitaries, excuse me. Yeah. So virtual motion is a very masterful way of interpreting what using group theory is doing to the practitioner. Yeah. But nonetheless, all of that being said, the way I've used group theory is different, okay? And as Carl has emphasized to me many times, the most obvious thing about it is that's different is that it's this very meaningful application of non-unitary groups, okay? And we're talking about collapse after all, and just like Austin asked before he left, he's like, well, is there collapse happening? Are things getting more pure? And the answer is yes, and ultimately things are getting more pure because when you multiply positive numbers, they just go somewhere. They don't like not go there. They either go to zero or they go to infinity, and being somewhere else is not going to happen. Yeah. Okay. And we haven't talked much about this, but for me, the principles of group theory, which meant a lot to Cartan, are these ideas of invariant differentiation and teleparallelism. It's just a way of thinking about, we haven't talked about right invariant derivatives, what H0 arrow means, but it means wherever you are in the 7-dimensional manifold, go that way. And that's like the sphere. We all know what go east means. So the sphere has teleparallelism. Yeah.
What do you mean by Markovianity here, though?
Yeah, Markovianity is because those Wiener increments were independent.
Yeah.
So the fact that we were reading squiggles is coming from the Markovianity of the measure.
Yeah, okay.
And that's where the right invariance comes from.
Okay.
So realizing that things live in a manifold, and then realizing there is a geometric interpretation of this multi-dimensional group because of the Markovianity. It's important to mention because I've seen in many textbooks, people have the vision that Markovianity is the same thing as the associativity of a group. So when you have Markovianity, you have a group property, but usually those visions don't go far beyond the idea of a one-parameter group, such as Lindblad's work.
Yeah, right.
So here we've got this 7-dimensional group that has Markovianity up the wazoo in this very meaningful way. And I put simultaneity here because I can't help but start thinking about time, future phase space, past phase space. These instruments probably could allow you to think about world lines. Like you can go back to relativity, think of a world line, wonder what if that world line was an instrument that was measuring the field in space-time as it was going. right? So then you have these notions again of simultaneity. What does it mean for things to happen simultaneously, etc.? So many questions to ask there that I don't have answers to, but I hope I'm conveying to you guys some of the big ideas. Hey, what else do we got? Ah, yeah, this is one of my favorite slides. The principle of psychophysical parallelism. This is a term that was used in von Neumann's original book, 1932. So let me read it to you. It says, nevertheless, it is a fundamental requirement of the scientific viewpoint, the so-called principle of psychophysical parallelism. There's no citation, by the way. I don't know who calls it that. More research to be done. That it must be possible to describe the extraphysical process of subjective perception as if it were in the reality of the physical world, i.e. to assign to its parts equivalent physical processes in the objective environment in ordinary space. Okay? So my interpretation of this is the following. So here we've got these things that are happening in the physical world, the sounds coming out of the radio, right? And meanwhile, these cross operators are telling you how to change what you believe about the system, okay? You can think of this row as what you think, okay? Bayesian updating is quantum Bayesian updating is a way a lot of people like to emphasize this sort of belief interpretation of this rule. So I'm calling that the psychology, right? And because you're changing in belief. And then there's this physical aspect, which are things that are happening. And there is a parallelism between the two, because I'm talking about this motion in a 7-dimensional manifold. And that's meaningful. It has all of these features to it, and it plugs into real space and time in a certain way. But where that manifold actually is it the physical part that has that? Is it the psychology? No. Okay, so there is this very explicit psychophysical parallelism in this idea of recognizing a 7-dimensional manifold in these simultaneous measurements. Yeah, so I told you guys a little bit about the famous von Neumann surprise of Har's 1933. And yeah, Cartan and Einstein spoke between 29 and 32 about what they were calling parallelism. So, it's amazing that the sphere has this notion of go east, and there are fantastic mathematical implications of that. Yeah, but this conversation goes very deep into how even general relativity has spacetimes with parallelism. And there's a retired professor here, David Finley, that I've been talking to, and yeah, he seems to have embodied the principle of parallelism. But I have yet to really understand how a curved spacetime has parallelism. I just think a sphere, group, okay, holding Cartan's hand. I think I get what's going on. But who knows how far this idea of instrument autonomy can go. Okay, let's see what else we got. What is this here? Oh yeah, so I was just telling you guys about how interested I am in this L dimension. So I haven't solved this whole differential equation. There's still these 2 other dimensions going on. And I won't bore you with the details. These are just ideas of how to actually understand what this term is doing in the remaining 2 dimensions. And I'm convinced that I can write down a Kalin-Szymanczyk equation, which is the kind of thing you have to write down when you do renormalization group for a field theory. I just don't quite know what I'm doing yet. Oh my God. So maybe that'll happen soon. Maybe it won't. Yeah. Oh, that's it. Thank you guys. Phew. Kudos. 2 hours. I'm happy to answer any questions.
All right, I've got questions. So I'll let someone else.
I've got a question from John DeBroda.
What do we got from John?
I don't even know if he's still here because he was at the airport, but oh yeah, he is. Okay. What are the consequences outside of the continuous weak measurement realm? We can measure non-continuously too, right? I suppose that doesn't correspond to one of your kinds of instruments. Indeed, so this idea of differential instrument is limiting me to these continuous weak measurements. Absolutely. So measurements beyond the differential, if I had any opinions about them, I've kind of lost them because I'm still just figuring out the one. Yeah. So do you have anything in mind? Like, yeah, if you have something in mind, John. Oh, CQuIC POVMs, of course. Yeah. Yeah. No, I am a big lover of continuity. So, you know, this whole thing about, I'm emphasizing that differential geometry is classical. It's not quantum. So I'm very much attached to these continuous dimensions, right? Right. Yeah. And so a CQuIC POVM is too fine. I mean, there's a finite number of outcomes in a CQuIC POVM. And I'm sure, you know, historically, when Lie groups were getting understood pretty well, then the groups of Lie type, the finite groups of Lie type started having a lot of progress at Princeton. And so I even bumped into a mathematician in an airplane once who was telling me about the breakthroughs that were happening in what, you know, finite groups don't have these nice diagonalizabilities as semi-simple groups do. But you could ask, when are elements of a finite group diagonalizable? And it took a while, it was like the 80s or the 90s before progress in that happened. So finite groups are trickier because they don't have Cartan decompositions. That would have been my first go-to, is maybe it has a Cartan-like decomposition. But apparently groups of Lie type and other finite groups, yeah, they don't have, it's even harder because, you know, groups of Lie, finite groups are sort of unitary. You need like many dimensions to have this idea of collapse going to infinity. So the CQuIC POVM maybe is the outcome of some, I don't know. Like these are all of my reactions to how on earth would this have anything to say about CQuIC POVMs.
Well, I mean, the coherent state basis is a basis. I mean, if you've got a POVM that gives you the coherent state measurement, you should be able to write down a different POVM, you know,
yeah,
some sort of convex combination of those things. Right?
Maybe, I don't know. I'm pretty tired at this point.
Okay, that's fine.
Yeah. Yeah.
Well, I mean, if the coherent state basis is a complete basis, and it is, you can write a CQuIC POVM in terms of coherent state measurements.
Oh, so you're saying a CQuIC POVM can be thought of as like a sub.
I mean, but you could, but there's still but the coherent states on the sphere are still in basis, right? They form a resolution of the identity.
They do, but that has nothing to do with the matrices you use. And so Carl is just attached to the Hilbert space independent nature of this program. Okay. And so if you're thinking about POVMs, I think Carl might criticize that that's a very Hilbert spacey thing. And you can't leave Hilbert space if you talk about CQuIC POVMs. But they're still interesting, and I think these things might have perspective. I don't know. But
I would make that point very strongly, but we do know that there's a representation of mesh2 in every space of every dimension.
Yeah.
Precisely because CQuICs are much less grounded concept. We don't know. Just don't know. And apparently it's going to need solving the whole universe to even know CQuICs exist. But you get a better structure by getting out of Hilbert space, where you get continuous, and all the questions that Chris Focus has about updating rules, they're all about P and the Q aren't the same, and we can ask the same questions. This is what I was hoping to explain to John yesterday. He drank his coffee faster.
Well, I just want to add that,
John, I don't know if you can hear, but like Carl is laying down the law of Hilbert space independence.
Well, and there's at the end, I mean, I remember from like photo detection theory, a strong measurement is built out of weak measurements at the end in an experiment.
Sure, sure.
Right.
And I can't think of the weak measurement.
No, come over here. That at the end of the day, strong measurements are built out of weak measurements.
Well, certainly that would not be Norman's for us.
Yes, but
it would be ours. Yeah, that would be the point.
But an experimentalist will tell you that, right?
Yeah.
That like you think your photo counter is just really doing things discrete, but you look at what it's actually doing and it has this like these electrical thresholds, right? And there's all this, it's fundamentally a continuous system.
I think it's an interesting question to ask. Is there a weak measurement that culminates in a sick POVM?
Yeah, I think that's
I have no ideas of how to start that. Yeah. But yeah, these differential geometric approaches are probably not going to help.
And they would not. And if you could show that,
they might, you know, Carl.
You would end up proving the existence of six in all dimensions.
There are these.
Therefore, you are not going to show that.
There are these very Carl. There are these very interesting pseudo continuities that happen in finite groups of Lie type. There's all kinds of really weird, it's like it's continuous, but it's a finite group stuff that happens. And so I'm far more open to, okay, you can't do differential geometry, but maybe if you understand abstractly what some of these things are actually doing, you could go beyond, still in a Hilbert space, but beyond, nonetheless. Who knows? Yeah, just in case somebody's having ideas, wouldn't want to discourage it.
Somewhat silly. I mean, but just to follow up on students, if you had never heard of coherent states, you would now know, since we don't have to do this for all semi-samples, you would now know what coherent states are for all the semi-simple groups and the no coherent groups. You know what coherent states are because they are the strong measurement that comes from measuring the generators weekly and continuously over time. So there's good limit there. And of course, would be incredibly interesting if one could do a similar thing for six.
Yeah, I consider it an accomplishment to have realized that the theory of complex semi-simple Lie groups, i.e. the Cartan decomposition, is so intimately related to the coherent state measurement.
Yes.
Right. This is new. It means something wonderful. It means a world line of things. Who knows what it means?
And the addition here to what coherent states is, you know this entire net of 7 dimensions. It's not 7 dimensions, we're all 7 dimensions. It's 7 dimensional basis. You know what that whole manifold is, and the boundaries of coherent state.
Which I have a nice picture.
By the way, John can't hear you. Yeah.
You didn't include my picture of exactly that, but that's okay.
Yeah, I told him good and that you're still talking, and gave him a funny face. Yeah. Are you guys? So he's got another question. Yeah. I can hear a little, but it's quiet from where Carl is. Yeah. He did move a little closer to the microphone. He is over there. As you can see, there they are.
It's the microphone on your computer.
Yes. Oh, yeah. The overhead's not good.
Yeah, yeah. Okay.
It never works.
Rather than a final, I recall there is some work about the Lie algebra that 6 generate. Oh, so John was thinking that the Lie algebra was the sick, and that there actually is work out there thinking about 6 as Lie algebras themselves. So indeed, interesting. So very different idea, because for me, the POVM is always the culmination point. But yeah, thinking about the POVMs as generators, that could be interesting. I just don't quite know what it means.
Yeah, that's a little
weird. Think about the sick elements as generators of the algebra there.
I guess so. Yeah.
I think what that's going to lead to is exactly the case. But it would be an incredibly interesting thing to analyze in terms of the ideas that that discuss.
Yeah, that could be interesting.
You will end up, if you pursue that program with measuring those generators, you end up with all of the states in your space as current states.
Yeah.
And the whole question is to me, what's the what's the group of the universal developing algebra?
Right.
And how much does it get distorted as you come down to SUD?
Oh, Jesus. Yeah.
I'm sure that's what will happen if you measure the 6 as generators. You'll end up with all the states because it's a complete set, minimally complete. And so it would be a great idea to think about what those are as generators of algebra. I'm just sorry, generator.
Cool. John, would you email me a link to that paper? I barely understood so he wants me to summarize what you said. I barely understood what he was saying because I was tired. He was getting really enthusiastic about universal covers. And I guess he was sympathetic to the idea that 6 as Lie algebra elements could be a good idea.
John was supposed to be away.
He's at the airport. I mean, he's been at the airport for a couple hours, so.
He's doing air travel in America.
Yeah.
You never actually go anywhere.
Yeah, you've been having a lot of bad luck with airport travel lately. Oh.
Actually, it's worse in Europe, so.
Oh, yeah. Okay. Oh, yeah, he had a 3-hour late. Well, how serendipitous this managed to fit in the 3 hours. Yeah, I did almost manage to completely fill it. Okay.
I think, in fact, that it's bound to be true that the right way to think of a complete symmetric set of generators for SUD is as the same.
Whoa.
That sounds right.
This is starting to sound like that. People were trying to do T-design measurements instead of spin coherent measurements. But there's no Lie algebra. Yeah. So it is true that, the Lie algebra can be thought of as a constraint for a universal enveloping algebra. So that's not a very Baker-Campbell-Hausdorffy way of thinking about Lie algebras. There's all kinds of interesting stuff to think there. Yeah. Oh, you sent me the link. Thank you, John.
Well, I think Chris is getting tired, so I think we should give Chris another round of applause.
Oh, yeah. Thank you guys for coming. Really appreciate it. Hope you had fun.
Marco, you're good to upload.
Bye, guys.
Yeah, great. Very good.
Thanks for coming, John. Thanks for coming on, Abam. Until next time.
Yes.
Bye.